Thank you for Chairman. Thank you, Chairman, for giving me the opportunity to present this work, which I has done with my colleagues from Mines Paris. So the main contributor is Tebib, which is not here. And we have the support of GRT Gaz with the presence of Maxime Bertin, and the contribution of the National Institute of Material Science of Japan with the contribution of Akinobu Shibata. So my outlines, so I will present a brief scope, a brief also description of hydrogen embrittlement. After I will present the cold spray process and the experimental setup used in this study, and the effect of the hydrogen embrittlement for vintage low carbon steel, and after I will present the effect, the benefit effect of the coating, and some conclusions. So the scope. So hydrogen is considered a promising green energy vector and an important alternative to fossil energy. So transportation and distribution of hydrogen fuel using existing pipeline steel network has been proposed as a potential low-cost and safety solution for delivering a large volume of hydrogen. For instance, you can see here so some figures of the network in France. So big networks and old one. The existing pipeline still are very sensitive to hydrogen, which causes a loss of mechanical property. So our study tends to prevent that. So we have many solutions. So using materials selections, better material, some solution using chemical inhibitors such as oxides, and the application of coatings, which is the purpose of this study. Hydrogen embrittlement is the loss of ductility and strength due to the presence of hydrogen. So the key point is the hydrogen trapped and transportation of various types, such we see in this specific session. So we are affected by microstructure, defects and porosity, and operating condition. With gas we have pressure, temperature and time. Here you can see an example of hydrogen-induced cracking of a line pipe steel. So the cold press process is a solid state coating deposition process where you have a supersonic nozzle here compressed with a gas using air, nitrogen or helium, and this powder is accelerated. And the typical size of this powder are in between 10 and 50 micron, and we have an impact of this particle on the substrate, and we get the coating like that. The main advantages is no powder melting, no oxidation, a high density, low porosity. We get a better fatigue life using that compared to another kind of additive manufacturing, because you have compressive residual stresses and ultra thick coating. Some application here along a lot of fields, we can get some additional functionalities. So you can see here some example, or some new functionality like you can repair, for instance, a structure. So here you can see the bonding. The bonding mechanism in the cold spray. So you have four main steps to understand what's happening when you have an impact of the high velocity of the particles. So the first step is the impact, and after you have the breaking up of the oxide layers from the particles and the substrate. you have the contact and of the free oxide surfaces and an extrusion, and after you have in the final step high deformation and high shearing, leading to the bonding. I have it miss here. I think a figure. Strange. No, I don't know what's happening. Ah, okay. Okay, so here you have a figure showing the deposition efficiency, because we have a velocity, a critical velocity below you have no deposition, and you have a window within this minimum velocity and a maximum velocity. After over that, you have an erosive effect of the particles, and you have no also no over that no deposition. So sorry for that. Okay, here the setup we used for our experiments. So low pressure cold spray machine. So the parameters are confidential. So you can see here some classical parameter for the kind of low pressure cold spray machine with an air pressure less than 10 bar. We use air, gas, and a short distance. Here the setup and the nozzle inside, so a chamber with a robot. So the experimental setup was done using electrocharging condition. Here you have the electrocharging condition with aqueous solution. With a poison and the current density of 3 ampere per square meter. We use low strain rate, around 10 to the minus 5 per second, and we use for the substrate material a low carbon vintage line pipe steel A42. Okay. Here the microstructure before hydrogen charging, so classical ferrite perlite microstructure. You can see some alignment of the perlite along the rolling direction, so L direction. Some inclusions, 2 population, so MNS, manganese sulfide inclusion, so aligned along the rolling direction, and a mixed population of inclusion composed by oxide, alumina oxides mixed with MNS. After hydrogen charging, you have here some degradation of the material, the substrate. Here some hydrogen-induced cracking inside the specimen, so crack along L direction, and some blisters at the free surface, and the texture has been evaluated by EBSD, and you can see that the main crack mechanism is transgranular. Some measurement by TDS have been done to get the hydrogen content. So here you can see the parameter of our measurement, 2 charging times, 72 and 90 hours. The diffusible hydrogen is constantly dissolved below the temperature of 400 degrees C. You have 2 peaks. I think it's related to the microstructure, because you have 2 population of inclusion and a specific microstructure of ferrite perlite, and a low content of non-diffusible hydrogen here above this temperature of 400 degrees. Here you can see the coating, which is So composite coating, you have 50% in volume of alumina. This alumina was chosen because of its low solubility of hydrogen and the low hydrogen diffusion. You can see here in this cross section the uniform dissipation of aluminum and alumina, the high density of porosity. We see no crack and no delamination at the substrate between the substrate and the coating interface. And inside the substrate, there's no crack. It seems that there's no. Okay, 5 minutes. Thank you. So the effect of hydrogen embrittlement on the mechanical properties. On the right side, you see here no effect on the tensile strength. UTS and yield strength are not affected by the charging, hydrogen charging condition, whereas the ductility is affected, and we have an effect of the time of the charging time, yeah, and we regain the ductility after hydrogen after coating with the same magnitude of the has received material. It's another way to show the results thanks to the ISTM standards, which define a parameter delta loss for the loss of ductility, and we have the same conclusion as before. To conclude, we observed also the fracture surfaces. Here you can see the uncoated and uncharged specimen, so a typical ductile failure with dimples. Here you can see the effect of the hydrogen, so with a mixed microstructure mechanism, rupture mechanism with dimples and quasi-cleavage. And when you increase the time of charged specimen, you can see less dimples and more quasi-cleavage. And here, when you put the coating, you see that there's no effect on the rupture, and we regain a ductile fracture as received material. So to conclude, we have a coating with a composite aluminum and alumina coating, which has successfully deposit with low porosity using this cold space process. So hydrogen embrittlement is greatly pronounced at high charging condition. The fracture surface mode from ductile to cleavage at 90 hours hydrogen charging time. So from the change from the ductile to cleavage. However, less cleavage was observed at less charging time, and the last conclusion is the slow strain rate test results reveal clearly that the coating exhibit higher hydrogen embrittlement resistance than the has received material. So thank you.